So I believe we are all joining at this time, so I can give you some of my experience about how to better utilize our Compute Canada resource. And it will be a really quick introductions and sharing. So uh, feel free to ask me any questions in the middle of my sharing, and I would be glad to help you understand better within my um, capabilities. So let me first share my screen, and I will also be sharing uh, the document link that I am preparing for us today. Um, so I will be sending this document link into our um, Zoom meeting room. So within this link, there are some other introductions like how to set up your Kaida computer account and what are the computing options, whether you are from Ontario Tech universities or whether you are from U of T. You can always refer back to this link to find the suitable computing resource that you need for your projects. So on in the latest document tab where I am editing and I'm still modifying it, uh, feel free to correct me if I'm wrong or adding some more information that you may find helpful for your um, some additional information that you think can be helpful for your colleges. And mostly I will be formatting this better so you can have a better overall reading experience. And I hope I can make it contain I hope I can cover most of the information that is important to you. So uh, just to repeat, the note that is based on my experience using Slurm computing, and I expect that you all have uh, successfully set up your Kada computer accounts, also uh, have some experience submitting some jobs using Slurm, right? Anybody here haven't got their Kada compute account or haven't done any job submission to Slurm that you might want to ask? Sorry, Prof. Andy, you are muted.
Oh, no, this is perfect. Go, please continue.
Okay, so given that we all have some experience with submitting uh, computing jobs to kind of compute, I will go through uh, some definition of group and user priorities that we might want to take a look into. So the most the most important piece of information you need to understand that we are all sharing the same computing resource allocations under Prof and his research groups. So that means if our research group have low priority, our queue jobs in general will have longer queue time to be accepted comparing to other research groups in Canada. So I made two examples that I captured from my screen to the document where you can check the fair share resource of each clusters. So you might also want to note that every cluster have different fair share and computing resources allocated to our research groups. So in case you are experiencing high queue time in DB cluster, for example, you might want to try switching to Naval or Fur or Roco to have better queue time. So this is the comment that I use. Oh, sorry. This is the comment that I use to uh, visualize to get this table of computing fair share for our groups and for myself as an individual users. So from this table, what you can interpret here is that the amount of GPU resources that is allocated to our research groups, which you can saw in the fair share column right in the pictures, in the picture. And the normalized shares will uh, give you help you understand that what is the proportions of our resources comparing to the whole cluster within the billing period. So for example, if the novel cluster have around uh, 10 years of GPU computing in the current 6 months, and it has around 10 different research groups that also using the same cluster, then each group will have 1 years of GPU compute, and the normalized share will demonstrate for you what is like the percentage of computing resource we are allocated with. The raw usage will help you understand that our group, how many computing resources in terms of second have our group uses cumulatively up until now. So the raw share will demonstrate value in years, but the raw usage will demonstrate value in seconds. So you might need to do some math to convert it back to years to understand how many resources our group have used. Or you can also relate back to the normalized usage, which also, if you multiply by 100, it will be the percentage of usage that we have used comparing to our allocated share on a specific cluster. So given the normalized usage and effective usage, we can calculate the level of fair share using the fair share algorithm uh, adopted by Slurm. Uh, so you just want to note that a fair share level that is greater than 1 means that we are being underserved, which means we are using less resources than we are allocated. So therefore, we will have higher priority comparing to other research groups. Therefore, our queue time will be shorter. But on the contrary, if our fair share level is smaller than 1, which means we are being allocated, uh, which means we are using more resources than we are allocated. Therefore, we will have lower priority, so that resulted in longer queue time. So that is research group level of computing resource allocation and fair share. Moving to user level. So right now you are only seeing one user, which is me. So the second line will demonstrate my priority within our research groups. So I have done the math here, so in case you want to take a look. So within our groups, I have been using around 0.1 accumulated years of GPU resource, which is relatively small. So my fair share level is greater than 1. So which means that I will have higher priority in terms of job queues comparing to uh, other lab members that have fair share level uh, smaller than mine, and vice versa. So that is on the novel cluster. Um, the number is really great because the need for A100 GPUs is less now since we have other cluster with H100 GPUs. So I believe some of you who are using Novel will have less experience in terms of long queue time and fast job acceptance. So uh, I think you should be fine. But moving along to uh, a second case where I uh, visualize the resources usage in NIBI. Oh, okay, it should be in NIBI. So in the NIBI cluster, we have access to H100 GPUs, and we also have RAC, the resource allocation competition, winning uh, GPU years that Prof and we have prepared the proposal and get the computing resources. Um, so with the RAC computing resource, you can um, it will be located in a different account, which is the starting with the RRG uh, prefix instead of the DEF prefix. Um, so you can take your time looking into the difference between the two resources type later. But what I want to share with you is the usage and the priority level. So in the RRG account, we are um, allocated with around 32,000 years of GPU computing resources. Uh, and you may see that our fair share level is still greater than one. So we are making use of our resources, but we are still underserved comparing to maybe other research groups. However, moving to the second line, you can see that uh, me personally, my fair share level is smaller than one, which means comparing to other group members in our research group, I am using more resources than possibly you. So if we are queuing at the same time, my job will be less prioritized over yours, and therefore I will have a longer queue time than you. So by sharing with you those informations, what I want you to understand is that um, our jobs queue time will be first determined by our research group priorities, fair share level. Then secondly, determined by our user level, fair share level. So if our groups have low fair share level, in general, all of us will be affected. So uh, our jobs, our research group jobs will have longer queue time than other research group jobs, and this might affect your deadline. For example, if you have a really urgent deadline for the upcoming ARR cycles. So uh, this just for you to note that we should try to efficiently make use of our resource as much as possible and avoid requesting more resources than we need for each of our jobs submitted to Canada Compute. Um, so according to my own experience, I find that the two main mistakes that I made when I first learning to use Slurm is that I was either requesting more computing resource than I need, or I haven't handle some bottleneck in my job scripts efficiently. So for example, if my jobs only require around uh, 32 virtual RAM memory, but I requested a full H100 GPU which has 80 virtual RAM memory, uh, that amount of GPU usage will also be counted toward our total research group billing. But at the same time, I'm wasting the remaining computing capacity of the H100 that I haven't used. So this resulted in lowering our research group fair share level, while we also haven't fully utilized the resources that we are allocated. And secondly, what I mean by inefficiently handling bottleneck, which this means that uh, for your jobs, after your jobs is accepted to the computing node, there might be some bottleneck that you should check, including either the model loading bottleneck or data loading. So we should try to avoid load and reload the same model many times within the same job durations. If, for example, if we go to evaluate a model on 3 different tasks, we should avoid loading it 3 different times, since it can take up some uh, computing time while the GPU remain unused. And also the same case apply to dataset loading. So how to make sure that we make use of um, the correct amount of computing resource and avoiding bottleneck. Uh, so my suggestion would be making sure that you understand what is the requirement for your jobs before uh, submitting uh, long duration jobs, for example. So this can be achieved by using Trillium login node GPU for debugging your jobs. So you can, if you haven't known, GPU login node provide you with 4 H100 GPUs for debugging purpose. So you can run debugging jobs on GPU login node as long as it is less than 1 hour, or so it should provide you some pretty comfortable space to run some tests for your jobs before submitting a long duration one. Or else on other clusters like NIBI or Roku, you can uh, request an interactive jobs using the S allocation command. So given these interacting jobs, you can debug your own jobs on an interacting command line, just to make sure that you understand how many memory required for the jobs, and uh, what are the number of CPU cores, for example, that efficiently boost the data loading process of your jobs, for example, to avoid data loading bottleneck. Um, but these two interactive debugging jobs can be inconvenient in some way. Like if you have other tasks you need to complete it, and you don't want to wait for the iterative jobs to be allocated, you can try to submit a short duration job first, and um, use um, the SACCT command after that job is finishes to check what is your um, computing resource utilization percentage that your previous job have made use of, given your registered computing resources. Um, After you have understand what are the computing requirements for your jobs, uh, you might want to modify uh, the your request of number of GPU cores or GPU type, for example. So an H100 GPU or an A100 GPU can be quite powerful for some lightweight jobs like uh, mm, quantized LoRa jobs or uh, small encoder only models. So in case you don't need to use the whole GPU nodes, um, you can try to request just an instant of the GPU. So for example, an A100 GPU allow you to request just a smaller instance of it, like only um, 1G and 5 GB means that we are only using 1/7 of the GPU computing performance, and also 5 GB of virtual RAM. So you can choose which option suit you best for your upcoming jobs that you want to submit to Cadre Compute. And for further detail, you can refer to each computing node uh, information on the Cadre Compute wiki, technical wiki, and it should show you whether uh, the current cluster supporting the current cluster support GPU instance or not. So for example, I will access uh, the Compute Cadre technical wiki and uh, search for raw core cluster, for example. So you should be able to find information about GPU instance somewhere at the end of the node informations. So in raw core, we are supported with 3 different type of instance with different computing performance and different virtual RAM to fit in your language models, for example. So we can choose what type of instance that fit our job best. Uh, However, GPU instance does not allow parallelism, so we cannot request like 3 instances at the same time. So in case you need to do like large uh, memory heavy jobs like continual pre-training language modeling task, um, will still need to request a multiple full GPUs node. But what you can further optimize is that you can um, try to compare uh, the efficiency of each uh, precision type computing using different type of GPU. So um, uh, the wiki gives a relatively easy to understand example in these sections. Uh, so you can take your time reading through it, and uh, yeah, I could leave it for you to investigate for yourself in case you need multiple GPUs environment. So that should be briefly what I want to introduce to you to better utilize your resources. Okay, so about the time for the jobs, I believe that uh, mm, don't worry about uh, if you are requesting longer time than it actually run. Don't worry about it because the total runtime, the final runtime, uh, starting when your job start and your job finish, that only actual runtime will be counted toward the group billing. So if you requested more time than needed, um, the only issue is that longer time job will have less priority when being scheduled within kind of compute slump. So you might further find information that there are different time duration jobs, that your jobs will be assigned to like 3 hours, 12 hours, 24 hours, or 72 hours. So 3 hour jobs will have more priority comparing to longer jobs. So shorter jobs will be accepted faster than longer jobs. So in terms of priority, if you request more time than needed, it will not affect our group priority, but it will only affect your queue time since, yeah, longer jobs will have longer queue time than shorter jobs. Okay, that should be all the information that I want to share with you. Is there any other questions? Feel free to open your mic and we can have a little chat, or else I can stop today's session, and uh, I hope you have some meaningful informations